Right, so the Earth's atmosphere is starting to accumulate oxygen from photosynthesis. And so it's life that is responsible for the current composition of the Earth's atmosphere. The Earth's atmosphere today is about 20% oxygen and about 80% nitrogen. The nitrogen was originally part of the Earth's atmosphere, but the oxygen was all put there by photosynthesis. And so it's important to understand how the life processes on the Earth were able to eventually control the composition of the atmosphere and therefore influence our weather. Okay, and so as time went on then, the oxygen levels started to grow. However, in the early environment of the Earth's oceans, there was a lot of iron. And so the oxygen reacted with iron initially to form rust. Also called iron oxide. And so at least for a while, the oxygen levels were stabilized and remained fairly low, while this reaction, this oxidation reaction with iron was taking place. However, eventually, all of the free iron was turned to rust. And so the oxygen levels could grow again. Okay, and as the oxygen levels increased in the atmosphere, it reacted with methane. Where did the methane come from? Well, this was the original gas that was produced by the early organic soup molecules that comprise the oceans. And so there's a lot of methane, and that was helping to hold in heat. Turns out that methane is what we call a greenhouse gas. And we'll talk more about that very soon. That essentially, the more methane you have in the atmosphere, it acts like a big blanket that holds in the heat that has accumulated on the surface. And that is why the temperature of the Earth was as high as it was in those days. But then the oxygen reacted with the methane because the oxygen levels are increasing. And essentially, this removes the methane from the atmosphere. Without the methane, the Earth froze. So this deep freeze is called snowball Earth. And this first snowball Earth event, we believe, happened about 2.5 billion years ago. Meanwhile, the Earth's interior is producing volcanic eruptions. Okay? And so the heat from the Earth's interior is very important in this evolution of the Earth's atmosphere. So this produces volcanoes, and the volcanoes have within them carbon dioxide gas. Where CO2 is our abbreviation for carbon dioxide. Now, carbon dioxide gas also helps to hold in heat. And so this process then allows for the snowball Earth to period to end. Okay, so we can think of the carbon dioxide atmosphere then as being a lid that holds in the heat. So the heat then tries to escape, that is prevented from escaping by the carbon dioxide gas. Okay, and we'll talk more about this in a little while. That this process of volcanoes releasing carbon dioxide gas is a way in which the Earth is able to regulate its temperature. So as things start to freeze, then the volcanic eruptions that occur can release the carbon dioxide gas. The carbon dioxide gas can then hold in the heat, and that can melt the ice. Okay? So that is one of the results of the heat being released from the Earth's interior. If we look up at the data projector, we can see a cross-sectional view of the inside of the Earth. We see here that the Earth has a solid inner core, a liquid outer core, followed by a rocky mantle, and then a crust. Okay, and this crust is where we live, okay, and that's floating on top of the mantle. But in the interior, we have the release of heat due to radioactive decay. And so that's the source of the internal heat that drives these volcanic eruptions. Then, if we look up again at the data projector, we see that this molten material that's produced in the Earth's core starts to rise toward the surface. This can generate the volcanic eruptions that we're talking about. And also, we have another consequence called plate tectonic motions. On the Earth's surface. So we can think of these plate motions as being very much like little pieces of cork that are driven around by a flame which is producing boiling water. So if we have these rising, what are called convection currents of water, that can drive around the pieces of cork on the surface that are floating. And similarly, the Earth has plates, and those plates are just pieces of the crust that are broken up, which move around because of the release of heat from the interior. And so these are different plates on the Earth's surface. These are different pieces of the Earth's crust, and they move independently of each other. And so in some places, one plate will dive beneath another. That's called subduction. And so here we can see how this might work. You would have a plate diving beneath the surface in this area, but then material would upwell in another place, what we call a rift. And the result of all of this, I'm not going to go into a lot of detailed plate tectonic motions here because it's a little beyond the scope of this class. But the result is important. We're starting to form continental land masses. All because of this plate tectonics motion. And so we look here at the Earth of today. It's not all ocean the way it used to be. Before this plate tectonic motion, you had enough water to completely cover the surface of the Earth, and we think that very little of the Earth's surface was above the sea level. It was all just water, a water world. But then the volcanic eruptions started. The plates started moving and gathering these land plates together, and so now we have about 30% of the surface is covered by land. And so this is the result of plate tectonic motions and volcanic eruptions, all caused by the release of heat from the Earth's interior. So this is influencing the atmosphere and therefore the climate. And so as time goes on in this very brief history of the Earth's atmosphere, we slowly accumulate more and more oxygen until we reach a point where a thermostat mechanism can start to kick in. You know, we probably are aware of the fact that a thermostat is a device that can control temperature. If things get too hot, the thermostat will cool things off. If the temperature gets too low, it'll heat things up. And so on the Earth then, we have instances of cooling. When things get too cold, basically what that causes is the Earth's surface to freeze. And then atmospheric CO2 from volcanoes can help to hold in heat. As I described before, ending the snowball Earth phase. But what if things get too hot? Turns out that the Earth can handle that too. Now the sun is getting about 10% hotter every billion years. And so this is a lot. And the trick in keeping the Earth's atmosphere in place and keeping life on the Earth going is to keep water going in the liquid phase. And so we want to maintain water in the liquid phase because we're basically big bags of water, and about 80% water, and without water, life as we know it is impossible. Okay, and so if the sun gets too hot, then what's going to happen is that the oceans will evaporate and we won't have any more water. And we believe this is what happened on Venus. Venus is closer to the sun and receives about twice the solar radiation that the Earth does. But we believe that in the past, Venus had liquid water oceans, just like the Earth does today. And so by looking at what happened to Venus, we can perhaps get a snapshot as to what could happen to the Earth in the future. And so here's the thermostat mechanism at work. We believe that Venus had oceans like the Earth. And probably had a thermostat mechanism like the Earth's. So here's how it works on the Earth. You've got the ocean. And then here you've got evaporation. And then that condenses to form clouds. The clouds oftentimes will blow over the land and rain. Then you'll get pools. Of water. And in those pools, what can happen is that minerals like calcium are dissolved. And so then the calcium reacts with carbon dioxide from the atmosphere. To form calcium carbonate, which is the same thing as limestone. Essentially then, the carbon dioxide is combining with calcium in water to form rock. Okay, and so the net effect of all of this then is to pull CO2 out of the atmosphere. So CO2 then goes into these pools and reacts with the calcium to form rock. And then this precipitate, in some cases, is carried out to the ocean. Sometimes it builds up in land masses, and so you get calcium carbonate layers on the bottoms of the oceans. But what this is doing, and this is the important and very significant part of this, is the removal of CO2 allows more heat to escape. Imagine that you're in your car and all the windows are rolled up and your car starts getting really hot. Or maybe you left it there while you went to the beach or something. You get back in your car and everything is just stifling hot. So what do? You roll down a window. And so essentially this is like rolling down the window. By removing carbon dioxide from the atmosphere, then more heat can escape. So we have a lot of carbon dioxide molecules. Then the heat tries to escape and it's absorbed by the CO2 and can't get out. So it's essentially then in the this lower part of the atmosphere, and the heat just keeps growing. But if you can remove a few carbon dioxide molecules, then some of the heat can escape. And so that can make up for the fact that the sun is getting about 10% hotter every billion years, because by reducing the amount of carbon dioxide, you increase the amount of heat that can be let out of the Earth's atmosphere, like rolling the window down. And then if things got even hotter, you could roll the window down even farther and remove more, analogously, more carbon dioxide from the atmosphere. And so this process then is what allows for the atmosphere to remain at a constant temperature. Even as the sun gets hotter, you can just remove more carbon dioxide. When things get really cold, then the oceans freeze over. You don't get the evaporation, you don't get the cloud formation, you don't get the rain, and you don't get the formation of calcium carbonate, rock, and so that shuts down that thermostat mechanism and allows the CO2 that's being released from volcanoes to heat things back up again. And so the process then of the thermostat mechanism is one in which the heat that's released from the interior is driving these processes by means of releasing carbon dioxide into the atmosphere and preventing the snowball Earth. But the reaction of the carbon dioxide molecules with water and dissolved minerals from rain is what takes and controls the levels of carbon dioxide that are in the atmosphere. So what happened to Venus? Well, eventually the carbon dioxide levels go to zero. And so that means once that happens, your thermostat is broken. And Venus could no longer cool itself. As the sun got hotter. So the result then is that all of Venus's oceans evaporated. And now we have what's called a runaway greenhouse effect. Where in the greenhouse effect, you have CO2 trapping heat. So a runaway greenhouse effect then essentially means that we've reached the point where the ocean's evaporated, and so then there's no way to control the temperature any longer. And so the temperatures start to grow. The water is also a greenhouse gas, and so that's turned into steam in the atmosphere of Venus. And then volcanic eruptions will still continue to occur. And so once the oceans have evaporated, the thermostat is broken. And the temperatures now on the surface of Venus are between 600 and 900 degrees Fahrenheit, which is hot enough to melt lead. So we might wonder then, well, could this happen to the Earth? And the answer is, we think so. We think that we don't know when it's going to happen, but we believe that this is an inevitable consequence of the sun getting hotter, and now our carbon dioxide levels are way less than 1%. So that means that we're close to that critical point where we could follow in Venus's footsteps. And if we don't do what is necessary to control the carbon dioxide levels that are being produced by our technology, we could speed this process up even more and end the situation in which the Earth's oceans exist in a liquid state.